some of the things we learned. And one missing piece is Morse theory on singular spaces. And it's going to be a very, how to say, soft version of Morse theory. It's a homological Morse theory. And to define a main quantity, I need to talk a little bit about local cohomology. So it's really fast. So we have a compact tame set, and S is a closed subset. What is the local cohomology of X with respect to S? Is just the cohomology of this pair. And what is the main role of local cohomology? How it's used in this micro-local theory of sheaves? We have this long exact sequence of pairs. So, if this happens to be 0, then this map is onto. And we say that cohomological classes in X minus S, in the complement of S, propagate over S to cohomological classes next. So they provide extensions. You can extend a cohomology class from the complement of S to the whole space. So it's obstruction to propagation. Now, I will define local cohomology sheaves. So local cohomology sheaves, let me do script S. They are the sheaves associated to these pre-sheaves. Okay. So this is the set U in here, and so I will denote by the stalk of this sheaf at X. So it's a Grady sheaf. And now it's easy to see that if U is outside S, this is going to be 0. This thing is going to be 0. So this local cohomology sheaf is localized along S, hence the name local. Okay, good. Now, there's a Crofton-type spectral sequence with E2 term. Let me just get the indices right. HP, X, HQS. So it's cohomology of P with coefficients of local cohomology shifts, and this converges to local cohomology of X. And I will be mostly interested in the case when these sheaves are supported at finally many points. So the stalks are 0 except at finally many points, in which case it degenerates right there. Let me just say what I proved here in special cases, you get the Floer complex. This is degeneration. It just basically tells you the Floer complex of a Morse function is computes the cohomology of a manifold. Good. Okay. And I will denote by HS of X to be the Euler characteristic and I'll work with real coefficients. Okay, that's the. By the way, when everything is tame, these objects are finite dimensional and they stop. So this is well defined. These are not pathological spaces. The good example to have in mind, a simplicial complex. They're all homeomorphic to simplicial complexes. So they're all. So on simplicial complexes, this is believable. Now here comes Morse theory. Well, sort of. Suppose I have f from x to r continuous and tame function. So everything is in some tame category. And I will use these notations, which I think you understand what it means. The part in x above the energy level c. Okay, so this is x, this is f, this is c, this is x, f greater than c. And all the other notations. Okay. Now, this is the type of closed set for which I will use local cohomology. So the first definition x and x is a homological critical point of f if the local cohomology sheaf with respect to this C is going to be the energy of the point x at x is not zero. Okay, that's what it means. Now, and I will say that f is nice. It's a nice continuous function if it has only finitely many homological critical points. Okay. Nice tends to be, nice is a probability 1 condition. Generically, continuous tame functions are nice. And let me say the only continuous functions I will look at, x lives in an Euclidean space, and I'm going to look at linear functions. There are restrictions to the set x. Yes?
So you were in a manifold setting. And
yes.
Critical point of index I, what would be local?
I will go through examples. I'll go through examples and I'll relate to Morse theory. Good. Now, why would one call these critical points? Well, let me state Kashiwara lemma, which, I mean, it's valid in a much more general context. But in the tame context, the proof is very simple. In more general topological spaces, you can see the proof in Kashiwara and Schapira sheaves of manifolds, and it's clever. I mean, I assigned it as a project in a graduate class. It was Bruce's student from Thailand, and I thought it was a page. I said, "A page, good." Now that page required to go back, introduce all sorts of concepts. So, and a page in that book is very dense. So Kashiwara. So this is we have f from x to r, nice function. Everything is tame, so I'll drop this attribute, and no homological logical critical point on the level set f equals c. Then, for all epsilon sufficiently small, the inclusion-induced morphism is an isomorphism. It's like the first result in Morse theory. If there are no critical points in a level band, then you have, in that case, homotopy equivalence. Here it's a homological level. So let's see why this is plausible. We localize in the region f greater or equal than c. Okay. And what it says, if you are at a point in here, the local cohomology is going to be 0, which means locally we can extend in this region. Not too much. But the point is you can do it uniformly up to c plus epsilon. Yeah. So if you take a cohomology classes in this tiny neighborhood, propagate a little bit. And what it says, in fact, they propagate cohomology classes from here, propagate up to a level of c plus epsilon. This is what it implies. The proof is not hard, and here I have hypothesis galore. I mean, the compactness and this, but at least it gives you an idea. So, X is compact, and S, and I'll work with compact. I don't want to. You'll see there's a very clever way to introduce non-compactness in the story, but I will work with compact sets. And so let me annotation BRX X0. It's X intersected with a ball of radius, open ball of radius X0. This sits in this ambient Euclidean space. So it's the ball in X with respect to induced metric. Metric in the sense of analysis, not in the sense of geometry. Okay. So we define the index of f relative to x at a point x0 in V. So we could be outside to be mx fx0 to be chi f greater or equal than f of x0. So its limit as r goes to 0, chi of the ball x0 intersect f less or equal than c. I should have said f here is a tame map from R, and f of x0 equals c. Perhaps I should draw a picture. I should draw a picture. This is a very good picture. Let's take, it's a star. Let's take X to be the star. And in all examples, I'll let F be a linear function. Okay, and it defines hyperplanes. Okay, and that's the direction of increase. What is this pair? It's the ball. It's the ball modulo the intersection modulo the intersection of the ball with the level of energy below C. Yeah. So in this case, that pair really looks like it's the same as cohomology of this and 2 points up to homotopy. Yeah. And the Euler characteristic is going to be Euler characteristic of this set minus the Euler characteristic set at 2 points. It's -1. And this is, let me say, this is always contractible. This is always contractible in a simplicial complex for small r. So what I get is 1 minus limit r goes to 0, chi of brx x0 intersect f less than c. In terms of Morse theory, what you get here is the unstable disk, a boundary of the unstable disk, if you think carefully. That's what it is. You look at a tiny neighborhood of the point, and you look at the part that has lower energy. So, like, let's look at the typical picture of a torus. What you're looking at, it's cohomology of this disk with its center removed. And that's just cohomology of the boundary. It's a homotopic. If you like, I like to think of it this way. I like to think of this as lower energy horizon. So you sit on the level of energy, C at a point x, and you look infinitesimally at points of lower energy. So you get the link, lower energy link of the singularity in there. That's what it is.
Just to make sure I understand, so this lower energy link in a manifold situation
would be
a sphere, right?
Would be the sphere.
The dimension of the sphere would be
lambda minus 1, lambda being the Morse index.
Yeah. So the indexes here are just plus or minus 1. They are not like the index of a Morse function.
No, it's not. This index here is going to be -1 to the power Morse index. This is going to be. And good. Excellent. And essentially, you have anticipated the question. When X is a compact manifold, F restricts to a Morse function, then this number is going to be Euler characteristic of a sphere of dimension lambda minus 1. So it's 1 plus -1 to the power lambda minus 1, if I'm correct. Am I correct? If it's a 2 sphere, it should be 2. If it's, it should be minus here. Am I? I realize it's a typo in this. I fell asleep. There's a typo in the notes. Okay. Okay. So if it's a two-sphere, that number should be, if lambda minus 1 is 2, it is correct answer. Yep. You get 2. It is correct. Yeah. So if you subtract this number, 1 minus this number, you get minus 1 to the Morse index. Okay? So this is going to be this index in here. Now, let me say a few things. Let me say a few things about nice functions where they do exist. They do exist for a simple reason. If X lives in an Euclidean space, which will always be the case, and then it admits stratification satisfying the Whitney condition, then a generic linear function is a stratified Morse function in the sense of Goreski and McPherson. And that's going to be a nice function. And the critical points, the homological critical points, are amongst the critical points of the function. There will be some, it is conceivable that there are critical points in the sense of Goreski-McPherson for which this local cohomology is 0. I mean, maybe it's not the case, but with singularities you never know. Okay. Let me give another example, which is very useful. Let's take a convex. Suppose X is a convex set, in the vector space V, and let's take C is a linear function. I will use the letter C to denote linear functions. Now, if I look at the level set, remember how we compute the cohomology. I take a tiny ball, and it's the cohomology of the ball modulo the part below. Okay, now both are contractible. So there's nothing going on. The only critical point is going to be the minimum. That's if you are here at the minimum. If you are here at the minimum, then in this definition, this is going to be the empty set, and this is not going to be 0. And this is the definition that I just erased. Okay, so the only homological critical point for a linear function on a convex set is the points of minimum. Good. Now, I need to say a few things about currents, and I'll be really fast, because I want to put things together and define the normal currents. And I mean, you know what currents are, but I want to just set up the notation and discuss sub-analytic currents. Sub-analytic currents are the currents that we teach our students to integrate upon. I mean, this is faces of cubes and everything. So if we have a X smooth oriented manifold, I have omega k of x compact. It's smooth k-forms with compact support, and the dual of this current of dimension k. Okay, omega lower k. Now there is a boundary operator, omega kx to omega k minus 1x. If you give me a current T, what is boundary of T? If I integrate a form over it, so in this part it will be forms. This is form integrated over the current. That's the same as integrating the differential of the form along T. So this is what we know. We know what it is, and that defines the boundary. That's just simple duality. Then there's a cap product. There's a cap product, and let me set up convention. There's a cap product for omega kx cross omega mx to omega m minus kx. If you give me a form alpha and a current T, I'll give you alpha cap T. And how is it defined? Define beta alpha cap T equals alpha wedge beta of T. So if you like, alpha, the operation alpha cap is the dual of the operation alpha wedge. Okay, in this order. Good. And a smooth proper map or C1 map between manifolds induces a push forwards on the space of currents. Now these currents may have non-compact support. Okay? And I don't need that. Now what is a Sub Anodic current? No, if I have S some manifold in X of dimension k, some manifold, need not be properly embedded, may have boundary, may be, think the unstable manifold of a Morse flow. It's a some manifold, but it's really disastrous. Yeah? And we have an orientation on S, then I have a current of integration, provided this has some locally finite volume to be able to integrate. If you think of the function, the graph of sine of 1 over x, then this is going to give you some headaches if you want to integrate.
Sorry, what was S compared to SK?
SK is the submanifold in X of dimension k.
Oh, it's not the case here. Sorry. Okay.
And this defines a current in X of dimension k in X. The integration current. And technically, and this is another place where Taine geometry is beautiful, if you work on an arbitrary manifold, you want to avoid weird things of like sine of 1 over x, because this has infinite length around 0, and if you want to integrate with one form that's supported near 0, you may get in some trouble. Okay. And you don't have this issue. You don't have this issue in Taine geometry. So now, what is a Taine current? Well, I'll tell you what is a space of Taine currents. Is the abelian group generated by currents like this, where S is sub-analytic submanifold. Okay. So how do I visualize this? Let me draw an example of a. Taine current of dimension 1. So I put orientation and then multiplicity 7. And here orientation and multiplicity -1. and so on. Which means, what is the current? If I take a one form, I integrate along this oriented path and multiply the result by 7, and so on. So,
what do you mean by the adjective analytic in this context?
Sub-analytic, sub-analytic.
What does that mean in this context?
It's a sub-analytic set, which happens to be a manifold.
Can you remind me what sub-analytic means?
Okay. Yes. I'll remind you what it is. It was, as an aside, after Jurasevich set up the theory of semi-algebraic sets, and the tameness of semi-algebraic sets is contained in this beautiful result called elimination of quantifiers. So what does elimination of quantifiers mean? What is a semi-algebraic set? A semi-algebraic set is something defined by finally many equations and algebraic equations and inequalities. Now, when you project, you get a set. You say project on over the real axis. You get a set, but if you describe the set, there are going to be quantifiers in there. The set points so that there exists something upstairs that go down. Elimination of quantifiers says this is semi-algebraic, meaning is defined by a number of algebraic equations in inequalities. No quantifiers is needed. No. So x in my okay. I will work in V. Or I'll work in V. Or sphere, unit sphere, V cross V. So there's no issue. Okay, so yeah. So people said, well, we could, and they say, let's try to define semi-analytic sets, and they thought quantifier elimination will happen there. And Hironaka observed, it's not working. You cannot eliminate quantifiers, and when you project, gave an example of a semi-analytic set, which when projected, is not going to be semi-analytic. So what he did, now that you know what is semi-analytic, what's sub-analytic? It's just a projection of a semi-analytic set. Okay, and remarkably, it works, but it took it's a span about 10-15 years to prove, in essence, that this is a tame structure, because these are the main results in this, and all the proof of tameness, according to Sergei, involve a form of resolution of singularity. A mild form of resolution of singularity. So you have some canonical forms near the singularity, you have some control. But I won't say more because I don't really understand everything. So these are, so a sub-analytic current in V is just a linear combination with Z coefficients of currents of integration over sub-analytic submanifolds. Okay. Now, the boundary of such a thing is also a sub-analytic current, which is not at all obvious. I mean, you can describe it explicitly what it is, but you need to produce a Weyl stratification and understand the normal structure. But it is this. What I'm saying here is a result of Robert Hart, Federer, and Hart. Hart did this thing. It's a famous papers in Octa in 74, 75, something like that. Now, I only want to mention one result, so-called slicing theorem, which for a geometer says you can do intersection theory. and in a rather geometric way. So what is, I'll mention just a special case that I need. So let's say I have X, a tame real analytic. I want to emphasize tame. The graph of sine X is not tame. Okay, so essentially it's a submanifold, some Euclidean space that is definable in the Sub Anodic category. The analyticity is not enough, just tameness. So it's a tame submanifold, analytic manifold, the same as Y. And let me give dimensions here, n and n plus k. Okay, so this is meant to have higher dimension. And I have a tame map. Okay, and here I have T sitting in here. Let me say T is a subanalytic current of dimension m in X. Let me just draw a picture. Here's Y. Y is just the real axis. And X, let's suppose X is R2. And the current is this. I want to put a vertical line here. And the projection F is, and F is the obvious projection. Now, I want to give a meaning of the intersection of the current, T. It has an orientation here. I want to give a meaning of the intersection of T with a fiber. I assume Y is oriented, X is oriented, and the fiber is going to be co-oriented. So I can do intersection in this. Now, F inverse of the point Y is also a current. It is also a current. Okay. In this case, the current is just this line, and geometrically, what I get is just a bunch of points of intersection in this picture. Here, if I take the fiber over this point, the intersection between the support of T and the fiber is one-dimensional. Now, in this picture, I expect the intersection to be zero-dimensional. Yeah, just curve and curve on R2, I expect to be one-dimensional. Here, the support of T is m-dimensional. This is dimension n. So I expect the intersection to be something of dimension m minus n. Yeah, that's what I expect typically, and typically this is going to what is going to happen. Now, the slicing theorem says that if the intersection between the fiber and the support of the current has dimension at most what is the expected dimension, then I can define this geometric intersection as a current. In other words, I can, in this case, I can add multiplicities to these intersection points, some numbers, and if I add these numbers, this is going to be the intersection, number of these homological classes. Okay, that's what it is. Here I cannot define. What is a novelty? This Federer did this in the 50s or 60s, slicing theories in the 60s. But it says this current is defined for almost every y. But you didn't know how, for which is defined. It says this is defined, and here's when is defined, when the intersection is good. So for example, if you look at the blow-up map from, you blow up a manifold, you blow up a manifold and you look at the total space of the blow-up and the projection downstairs, there's only one point that the fiber has the wrong dimension. And typically this is what happens when you have a wrong dimension. There's some blow up happening in there, and there's descriptions. And now, so if the dimension is what you expect, then you can give a meaning to this current. And moreover, outside a hypersurface in y, the points outside a certain hypersurface, the fiber intersect in the right dimension. Okay. So it's more than almost everywhere is defined. There's a discriminant locus. So outside the discriminant locus, the intersection has the correct dimension. Okay. Now this discriminant locus could be really ugly. Many connected components. Got it. Well, these are manifolds, but this is not a manifold.
So you get discriminant locus.
You could call it discriminant locus, but there's a theorem that says the locus of points where this is ill-defined is a tame definable object at strictly smaller dimension. And definable, you should think of it as described by some equations. So everything is definable. Good. So now that I have this, let me state a uniqueness theorem. So this uniqueness theorem was first proved by Joseph Fu. He's in Athens, Georgia. A while ago, about 20-some, maybe 30 years ago. And it's really long. Believe me, three papers added up for about 150 pages. But in the tame category, it can be done in 4 pages. It's really, and that's the only place you really can apply the theory. So here's, I'll draw a picture. This is our vector space V, and this is the unit sphere in the dual. So what I'm depicting here, unit cotangent bundle. Okay, so this I have here S V star cross V. That's the manifold. That's as real analytic as possible. And here I have a set X. Okay. Now I have a map, a projection going this way. So let me call it pi from S V star cross V into S V star. Okay, it's a projection onto this. Here, the fact that the cotangent bundle is trivial in an obvious way allows us to make this. Okay, now what are here? What are points in here? They're linear functionals of norm 1. And for generic in the sense, in the complement of a tame thing, Xi is going to be a nice Morse, a nice function on X. Okay? And let me define the following current. let me define the following current, delta xi x, to be sum over all the points x and x, mx minus xi x. So that's the index of the Morse function minus xi in x. Yeah, it's just the Euler characteristic. And I'm sorry, and this is a delta function, xx. I should put here a point p to emphasize it's a point p. So this is a current. This is a zero-dimensional current in SV star cross V. So this zero-dimensional current, it's a catalog of all the critical points of the Morse function minus xi, together with their indices. Yeah. Good. By the way, if X were a smooth sum manifold, let me tell you what this current is. We discussed in the first lecture. Is the intersection of the fiber of pi with the conormal bundle of X. We just proved that. The unit conormal bundle of X. That's we proved that. Good. So here's Fu's uniqueness theorem. Fu's uniqueness. So we have V Euclidean space. Let me put capital N is its dimension. X compact tame in V. And let me stick with the notation. So there exists a unique current, and this is a current of dimension n minus 1 sitting in S V star cross V. It's sub anodic current, which is a cycle. It is Legendrian, so alpha is the contact form, so alpha restricted to n is 0. And n intersect the fiber of xi is going to be this Morse current. For almost every xi. This is for almost any. Okay. I mean, it is not surprising that it's unique, because I'm requiring quite a bit of properties here. This seems nearly impossible, but we know that such things exist. And one example is the unit conormal bundle of a submanifold. In another example, you take an open set in V with C2 boundary, and look at the unit outer normal. That's the Gauss map of this hypersurface, and then define n to be the graph of the Gauss map. And it satisfies all these conditions. The uniqueness, it's very clever. And I mean, all the ideas are in Fu. What I've done, observe that I don't need to do all that work. It's just keep track. It's a little bit of some clever symplectic geometry, elementary symplectic algebra that works out. Good. Now, existence. These things exist. And uniqueness will play an important role in the story. So for every compact tame set, admits has a current like that. It's going to be the normal current. It could be called normal current. So such things exist. So let me give you the idea of the proof. Is very geometric. Let's suppose X is compact tame set. This is X. Now one can prove, thanks to logicians, that this is the zero locus of a C2 tame function, which is non-negative and proper. For example, the distance to the set X would be such a thing, but it may not be C2. So, but there exists. Everything is a locus of this. So I have a function f from v to 0 infinity, which is C2 function proper, and X is the zero set of that. Now, look at the region where f less or equal than epsilon. Now, this is going to be where f strict epsilon for all epsilon sufficiently small are regular values for the function. So the boundary is going to be a C2 hypersurface. And this is an open set with a boundary hypersurface. We know how to define the normal cycle for that. So this is an aura. This is x epsilon. So basically x epsilon collapse on x0. So x epsilon has such a normal cycle. What is it? It's just the graph of the normal of the Gauss map. It is a current, and as epsilon goes to 0, this converges to a current satisfying all these properties. So this is the existence. Now, so you see the normal cycle, this object, the normal cycle is the graph of a possibly non-existent Gauss map. Now, what's important about this, and this is why you can do computations. If you tolerate me one more time, I can explain how to do these integration with respect to Euler characteristic, inclusion, exclusion. I'll prove Schapira's result about Motivi-Gradon transforms. That's when you have applications. I'm done with the theory. I feel that now I rush it, and just at the moment where the chocolates are in. Thank you.
Any questions?
So we proceed next week.
Yeah, I mean, if you tolerate me, I can do one more week.
Absolutely. Absolutely.
Yeah. Because, yeah.
Thanks again.
Welcome.
Well, I don't want to stop any other questions.